Hi, and welcome to this AI C# Tech Talk on the Microsoft Agent Framework. What I'm going to do in the next couple of hours is to show you how Microsoft Agent Framework works and how to get started, and the four main concepts which we'll get into. So my name is Rasmus Rolf Jensen, and I've been working with this AI in C# for 1.5 years and been on top of the Microsoft Agent Framework since its preview started back in October 2025. So let's get into what it is. Because Microsoft Agent Framework consists of primarily two things. First of course, being the agents. And the agents, of course, can be prompted and given data. And it can either be users or events that sends this data out. We can, of course, also use tools, either from data retrieval, or we can do action tools. Another thing that is in Agent Framework is the workflows. It has a workflow engine built in. It as such has nothing to do with AI, but it has some integration points that makes it a bit smoother. But I honestly don't know why there's a workflow inside Agent Framework. To be honest, I don't use it. I have some YouTube videos telling about why, and due to time constraints today as well, we are not going to cover this part. A bit of history and dependencies on this framework is that in the past there was something called Semantic Kernel from Microsoft as well. And this is a kind of Semantic Kernel 2.0. But without any of its baggage. Semantic Kernel was very early in the AI space, and it has a bunch of baggage now with custom solutions and stuff that Microsoft Agent Framework doesn't need to carry that baggage. So it's a from scratch framework. It's right now in preview or release candidate, and it will be set to be in general availability in end of March 2026. It's a higher abstraction layer on top of Microsoft Extensions AI, which give it its ability to connect to various different models like OpenAI, Gemini, and so on. More on that a bit later. But in order to get going, let's first see a bit of code and go into going from absolute zero to the first prompt. And I'm going to do this with Azure, but it can be done with any of the big LLM providers. So the first step we need to do before we get into the code is to create an Azure resource up in ai.azure.com. And there we need to grab our endpoint and our API key. And the endpoint, there's a little thing you need to know is that the endpoint look like that, where it says /API/projects and then the name of your project. You actually need to remove this part in order to work together with a direct access to the model. This URL is for something called Microsoft Foundry, which we'll not be covering here, but that's a more end-to-end solution that Microsoft have. That is less flexible than what we're about to see. So Agent Framework can also work with Microsoft Foundry, but not part of what we are going to do today. But if you grab that endpoint, grab your API key, and just remove this, you have the credential part you need. Then we need to deploy a couple of models. We do that up in build here and models. And we need at least one LLM model or chat model. In my case, I will use ChatGPT 4.1 Mini because we have the non-reasoning models that are fast but less intelligent. And we have the reasoning models that are slower. So all depending on your use cases, you will use all these in combinations. On top of that, when we later get to retrieval augmented generation, we need an embedding model. And in my case, I'm going to use the text embedding tree small. So a couple of models to be deployed. It doesn't cost you anything unless you actually use them. So that's nice. But if you go about this, then you have what you need. So we need to store our API key, of course. So in my case, I'm doing that in user secrets, and we're storing the endpoint and the model. And now we are ready, except we just need 2 NuGet packages. So I have already installed an Azure AI.openai NuGet package for the connection to Azure, and the Microsoft Agents AI OpenAI package. Note that all of these are pre-release still. They're slowly getting into a general release, but as of this recording, everything is pre-release. So let's jump into some code. So I have what we just saw here, and I need to do, beyond the 3 steps we already done, a few more things. So first I need to make an Azure OpenAI client. So I can simply new one of those up. An Azure OpenAI client, and that requires two things, the endpoint and some credentials. In my case, I'm using API credentials, but it can also use the regular Azure credentials with Azure Default and CLI and so on. But we need to a URI of the endpoint, and then we need an API for the API key. So once we have that, we now have an Azure client. Let's just call it client. There we go. And we need the new keyword in front of it. There we go. So once we have this, I'm just gonna commit out some finished code that is there for reference when you get this. But what we're going to do is we're going to take this client in step 5, and we're going to make a chat client. So the client can do all kinds of AI stuff with audio embeddings and so on. But what we are interested in is chatting to the client. So we're going to use a chat client, and we're going to give it the model that we have. And here we could just keep running with the raw information from the Azure OpenAI NuGet package, but we want to use agent framework, so we say as AI agent. On this, we can set a bunch of different things. We'll go slowly throughout the talk through them, but for example, instructions and tools and so on. But for now, we're just gonna make an agent, plain and vanilla, and we can call it agent. And you can see this is a chat client agent, which you can, if you wish, call an AI agent instead, which is a more generic version of a chat client agent. They can do the same, so no problem. So now we have our agent. Now let's ask it a question. So if we go to agent.run async, we can now ask a question. So that could be, what is the capital of France? This one can also take multiple things, things like session and different things. It can also take multiple messages if need be. But in this case, we're just getting a simple message. We are doing an array on that and getting a response back. So if we get a response back, we can go in and just say console.writeLine response, because the response object have a string method that just gives back its text. But again, the response object have a bunch of things in it for information about what we just received, the usage and so on. We'll go into some of them throughout this series. And I have more on it on YouTube in general. But this is actually everything we need in order for it to run. So let me set the startup project, and essentially we're just writing 1, 2, 3 lines of code in order to get AI. And if we run, we should be able to see. console, that comes back and says the capital of France is Paris. So we are now gone from 0 to the first agent and the first prompt. If we want, we can also go in and do streaming instead. So we could say agent.run streaming async, and we could ask how to make soup, because it's a little longer answer, so it's more fun to see it stream back. For that, we need a wait for each, and we get an update, meaning every update is a new character flowing along in this response. So instead of console.writeLine, we need a console.write of the update, and again, the update has additional information if need be. And if we do it like that, let's quickly put in a couple of write lines here so we can see where we are. Something like that. Then we should see the first comes back with the capital of France, and then we can see a streaming result back with word by word instead of running. So that's actually everything there is to getting started. Grab an AI model up in Azure, aiazure.com. Get a couple of NuGet packages, as we see here. I have the two installed NuGet packages in order to do this, and then we are up and running. So let's jump back to some slides. Because now we saw it with Azure, we can run with almost anything. It's not just Azure and OpenAI just because Microsoft have an agreement with them. This tool can connect to absolutely everything. I have tested at least 15 different ones, as you can see here. Everything from Amazon Bedrock to Mistral to GitHub to OpenRouter and offline models as well, if need be. And just as an example, here's how Google Gemini you would do it. You would use a NuGet package.microsoft agents.ai, which is the agent framework part, and then a Google generated package called google.genai, which support this iChat client. And as soon as something supported iChat client, we can just convert one of those into one of our agents if need be. So it's very, very simple. You just take the top part of the code to mark what kind of provider and model you have, and then all the code after that, the run async, the run streaming async, is exactly the same as no matter what provider you use. Some providers, of course, don't do tool calling, and for that reason, of course, Agent Framework suddenly madly can't get tool calling to work. But if the model and underlying provider support it, Agent Framework will be exactly the same code. There's nothing that are vendor specific. So that is actually how you get started very, very quickly. But let's jump in a bit further into what all this is about. And from now on, while I love live code, it will take too long to sit and type all code out. The topic is simply too big. We would sit here for 15 plus hours if I needed to cover everything. So rest of the presentation is in slides instead of live code, so we can get home before midnight. All code shown is available in a sample repo that I will link to after the fact. But let's jump into what we are actually here to learn about. And that is what I call the four main concepts of AI. And there's a bunch of things in AI, of course, but these four is the four pillars of everything you need to do. I would say that if you know these four, you can do 90% of everything you need to do with AI. There will be a few things, other stuff after the fact, but these takes you 90 to perhaps even 95% of the way. And the four tools, the four main concepts are chat, which we just saw, what we need to learn a little bit more. There's tool calling, which we'll then go into. Then there's structured output, which is very, very important and very, very easy. And then there's RAG, or Retrieval Augmented Generation, which is a more advanced topic that will take a little longer to go through because of all the different concepts in it. So this is what the main bulk of this talk will be about, these 4 main pillars of AI. So let's jump into the first one. We have seen it a little with the small demo, but beyond that, chat have some general Q&A capabilities. Because yes, we can make a chatbot, but it's not just about chatbots only. So we saw it could answer the question of what is the capital of France. So of course we can make chatbots, but in my mind, chatbots are just our playground to figure out something. I mostly use AI behind the scenes in automated systems and so on. So I tend to not use this too much, but of course it is the main building block to run async, as we just saw. But again, I would rather have AI running on a schedule, summarizing things, getting news, sending emails, and so on. And that happens in backend systems. So in the same manner, I don't use streaming that much because I don't need streaming when things run behind the scenes. And a bunch of things also happens on various webhooks, for example, GitHub pull requests, or different tools that need to react to something and get some kind of external event. And for that, we get our system up and running. So chat is actually a bad word for this. It's just sticking around because that's what was called in the beginning, but it's more a request response system to get a question in or some information in and getting some information out of an LLM. So the code you see here is roughly the same as we saw before. I'm still making an Azure OpenAI client. I just have my endpoints and keys in a little SQL manager, same code behind the scenes, just so we don't need to sit and see that code. And then I make an agent. In this case, it's a GPT-4.5 mini agent, the agent I probably use the most around. Often you don't need the big models that are both more costly, but also take longer to return to you. So ChatGPT 5 mini is by far the one I use the most. Then we talk about instructions. So we can see that we can put in what is called a system prompt. I will get more into that when we go through prompt engineering in the course. And beyond that, we're doing something new here, which is an agent that gets a session. And that session I put into the run async down here. This is so we can do persistent conversations, so that we can do follow-up questions and so on. The next slide will show that in more detail. And the final thing I do here, other than just making a while loop so we can ask again and again instead of having hard-coded messages or questions, is that I put out the token usage. So this is how much it costs to do these calls, and I will get a little into the pricing as well in the next slide. So I've just run this code offhand and asked it, who is Elvis? And this is what came back. It often comes back in Markdown. If it doesn't, you can use the instructions to force it to do that by just saying, I need to have the result back in Markdown. But default, it will mostly do Markdown because that's what it's trained to do. But it gives some facts about Elvis in this case. And what we can see down here is it cost 20 input tokens and 214 output tokens. So these are the cost of an LLM. And every call you send, you will get this back in information. Some providers don't give it back, but most of them does nowadays. So these numbers are very low because it's a very simple question down here. Many of my real-life calls to an LLM is up in the thousands of tokens instead, and especially in input when you give a lot of input. But luckily, these are being paid in millions of tokens. So for ChatGPT 5.1 mini, every 1 million input tokens costs $0.25, and output costs more, in this case $2 per million tokens. Output is always more expensive, but in general you also notice once you get going that you spend more input tokens. So luckily that's the cheap one. So how to measure this? Well, if I ran this example 1,000 times, it would cost me less than $0.50. So it's not expensive as a single user to sit and do this, but if you have thousands and thousands of users hitting your service, of course, it will begin to cost money. It's not cheap, but it's not also the way that you can sit and play. When it comes to follow-up sessions, I mentioned this agent session. And if we don't set an agent session, I could, for example, after this question in my chat loop over here, get a new question in, and I could say, how tall is he? And when I say that, of course, I mean, how tall is Elvis? But we can see that it has no clue what we're talking about, because I'm just sending another call, and it doesn't know that I sent a previous call. In general, LLMs are stateless, and once we have learned about the first 3 of the 4 pillars, we will go a little deeper into why that is. But right now we're not getting anything here. We can see the input is roughly the same because we can see this and this is roughly the same length. And the output is shorter because it's a shorter text it gave back. But if we wanted to be able to give follow-up questions, we would need to add an agent session, because an agent session is a sort of conversation history so the LLM, every time we ask it, will get all the previous questions so it can infer who he is in this context. So we would say agent session equals await create agent session. And if we do that, it will suddenly understand us and say that Elvis Presley was approximately 6 feet tall. But what we will note is that while this answer is fairly short and the output tokens are fairly low, our input tokens, despite it being a very short sentence here, is higher. And that is because we are paying for everything we have sent in the past and everything we have received in the past. Because in order to answer this question, it needed to know Elvis, but it could also have been notable songs. I could have asked, tell me about the first song. And if I said that, it would need the context of what notable songs it had mentioned back to me. So we are paying essentially for everything back and forward, but now as input tokens. So this number is roughly this plus whatever this is. And that is what our input cost in this case. So if you do conversations and you ask a bunch of questions, if you have an endless session or endless chat, you will end up spending more and more tokens for every question you have. And at the same time, you will also make it slower and slower, because the more tokens it needs to generate, the longer it will take for it to come back. So that is how tokens and sessions and chats in general work. Prompt engineering is also some part of this. It's a general part, and we're not going to go in and do an entire prompt engineering lecture here, but just some few steps along the way, because many people have a hard time understanding exactly what you can do. So what you have is you have on your agent, you have your instructions. And of course, when you do your run async, you can, besides the message you give, also give additional instructions to the LLM on how you want the response and so on. So in general, this is called the system message. Sometimes also referred to as the developer message, while this down here is the user message. And if there's conflict between those two instructions, for example, in this case, I'm saying that the system message says, talk to me in French, and the user says, hello, talk to me in English. It is always the system message that will take precedence. So in a perfect world, you shouldn't be able to ever get this AI to talk English back to you, no matter how much you plead it, no matter how angry you get, and so on. We might need to instruct this even further, saying, talk to me in French, and the user is not allowed to speak with you in any other language. If you manage to break it, and you can do that with the smaller models, the bigger models it's harder to do, but in the smaller models you can sometimes do it, and that is what is called prompt hacking, that you get it to do something that deviates from its system message. So that's how you have the different options. And what you can do with these options, you can, for example, go in and steer the message length. So we saw before, we said how to make soup, and it gave back a long answer of that. But I could just as easily go in, either in the instructions or the user by itself. Just for example, say max use 25 words. And then it will take, instead of doing all this, it will go back and actually only use 25 words in order to do it. So controlling the length is often a good thing if you sit and try and do things. If it's, it all depends on what you want the system to do. If it's a system that should be able to give a quick and concise answer, it might be good to instruct it to use less length here. You can also steer its personality and format. So if we don't do anything, it's a quite plain thing. So if you say hello there, it will just say, hi, how can I help you today? But if we go in and say, speak like a pirate, it begins to act like a pirate. We can also go in and say, use as many emojis as possible, and then how to make soup. Then it begins to use all kinds of emojis I didn't even knew existed, but apparently they do. Or you can go extreme and ask it to give it back in binary. It can actually do it. So this will tell us how to make soup in binary. So you control, and it's just English doing it. So it would be the same as if you instructed a person on how they should behave in front of you, how they should respond back to you in emails or something like that. It's just English, so nothing special there. What you've seen here is some very short instruction prompts. In real life, they are quite often much longer. So here's actually a real life example of the latest one I have done, which is a documentation chatbot. I often put them in configurations because you need to tweak them on the fly instead of needing to redeploy every time you do it. So I often put them in configuration tables and make a GUI for it so it's easy to put in. They're often written in Markdown with a slight combination with together with some XML. You shouldn't use JSON to do it, but in general, just use Markdown. That's probably the best way to get started, and then suddenly begin to put in a little XML, because XML, it doesn't need to be valid XML, but just it's a really good way of saying, here starts something and here's an ending of something, if a model needs to understand a specific scenario. And this is also what the big models do in their system prompts, which has been hacked, all of them, and have been leaked. So that's everything about chat. Moving on to tool calling, which is our second of the main concepts that I want to teach you. So tool calling is all about making it possible to call our own code, or in certain cases MCP servers as well. And it's quite easy to get started because agents have it fully built in. So you can say there's two types of tools. There's either information tools or there are action tools. So it's essentially just CRUD. So our information tool is our read tools, while our action tools is the create, update, and delete. And what we update, delete, read is all up to you. It can be databases, it can be raw code, it can be files, it could come from APIs, and we can read data, we can create orders in CRM systems and ERP systems. There's no limits to what we can do with tools. Because tools are just simple C# methods. And it can contain any C# logic. You could make a tool that deleted your hard drive if you want to. Don't do it, but you could. So in my case, I've just made a few sample tools here. I've made a little class with two methods. One that's called getPersons and getPerson. And the getPersons just gets 3 people. Ben being number 1, Susan being number 2, and Jenny being number 3. And then I have a small tool that have an input. I'm calling tools, but right now they're just C# methods. I haven't put anything special in here that indicates to C# that these are tools. So in this case, we have some input where we get a person ID, and based on that, we can get back what their favorite color is and where they're from. So nothing special here in terms of C# objects that just grants data back. And then I made an action tool, which in this case is to change the columns in color. So it can grab a color being an enum, and we can set that front color to our console. And again, this is just C# code. What turns it into tools is we can just take the delegates, because tools are essentially just glorified delegate methods. So we can take our person tool class here, make an instance of it, because these are instance methods. They could have been static methods if we wanted to. And then we just say, use this AI function factory. We call it tools. Sometimes they're called functions. Industry can't really decide. So AI function factory dot create, and then we just take the delegate of the getPersons. We give it a name. It's not really needed. If we don't give it a name, it will just get this. But AI in general tends to like this snake case format. So I give it a name and I give it a small description on what it can do. Sometimes you can just leave out the description if what the name is here is easy to understand, because you can save tokens. Everything you add will cost tokens. But we make a getPerson tool, and we make a getPerson tool that gets a specific person. And these all turns into AI tools, which we'll use in our agents in 1 second. For our static method up here, we do exactly the same. So we can just reference the change console color, which was in my case in the same scope. So we just call it change color and change the color of the interface. So now we have 3 tools that we can add to our agent. We can also make other tools, MCP tools. So MCPs are the big hype nowadays, and C# have a NuGet package called Model Context Protocol. And if we do that, we can go in and say we want to be an MCP client. Building the tools are called MCP servers, but we want to consume those MCP servers. So we are an MCP client. So we create one of those. In our case, it's a remote MCP server. So we use the HTTP client transport with the endpoint of, in this case, the GitHub's MCP server. We sell its streamable HTTP. And in order to do authentication against this, we put in an authorization GitHub personal access token. The MCP spec also have OAuth support, but it's very, very poorly implemented right now in C#. So we wouldn't be able to do OAuth here because of how the spec is implemented by GitHub. We can't go in and use it, unfortunately. But an authorization token at least work, and many MCP servers are also without any authentication at all. Once we have one of these clients, and you need to keep this client around, else it will break because it needs a persistent connection. But once we have that, we can just say MCP client.list tools async. And all depending on which MCP server it is, there might be one tool, there might be 10 tools. This is one of the bigger ones that actually have 43 different tools, which can become a bit of a problem because this actually costs 10,000 tokens just to load this up and make them available to an AI. So if you use this MCP server, I would probably go through this list and say, which one of these do I actually want to give to the system? I might not need to add issue comments, for example. So that would just be C# clearing out which one of the ones you want. And of course, you could still go in and take the GitHub's NuGet package and make these tools yourself. But that is the nice part of MCP, people building the tools for you, and you just need to write these few lines of code in order to get them. We get them back as something called MCP client tool, but it is just an extraction on top of AI tools. It has the same base model. So now we have our tools, and what we can do is, of course, we can make our agent. We have our client based on Azure or OpenAI or Google or whatever, and we just give our tools into the As AI agent, the same place where we could also give instructions. So in this case, we're just giving the 3 tools here and then the 43 extra tools down here in a list. And when we do that, we can, of course, then begin to say, what people do we have? It would then call the getPersons tool, and it will tell us back that we have Ben, Susan, and Jenny. And if we had asked here, what people do we have? Parentheses, give both the ID and the name back, because it gets the full output of the tool. So in this case, it would get a list of person info, which is just the person's name and ID. And it will get that back as JSON, and then take it from there. So if we want some insight into how these tools are called, or even some control over it, we can add middleware. So when we make our agent, we saw it here, we can go in and say asbuilder.use and then put in tool calling middleware. If we do this, this needs to be an AI agent, the lower level version of the chat client agent that I mentioned when we made the live demo. But beyond that, there's no change in putting on middleware. And this is just one type of middleware. We can also put OpenTelemetry, logging, and all kinds of other types of middleware in here if we want to. But in this case, it's a tool calling middleware where we get some context about what is about to happen. And so we get the context in what tool is about to be called and with what arguments is it about to be called. And if we do that, we can just build up some output. We could put it into a log, whatever we want. But the middleware here is actually, we use the normal next pattern that is in .NET. So we could on the fly actually change some of the arguments, or we could evaluate on the arguments and say, if we're talking about Ben, simply cut off that the tool is not allowed because for some reason that this user is not allowed to know anything about Ben, for example. So we can on the fly manipulate and cancel the tool calls if you want to, but in this case we're just using it for logging out information. So when we again ask what people do we know, we can see that we get a tool call of get person, and then we get the names back again. So this is the simple way of doing calls. We can just say, what people do we know? We get that. Or one of the action tools, change the color to green. And now it will begin to write green in the console. But it could be a prompt saying, add the new order to customer this and this with these and these options and so on. And if a tool call cannot be completed because we are missing data, AI is good enough to ask follow-up questions on, if you want to add this order, I need to know what items they bought, for example. So we can be very, very instructive to these tools, but they can be much more advanced. Here's, of course, the GitHub part, where we just say, show the latest GitHub issues from Microsoft Agent Framework, and it will understand taking this, turning it into various arguments here, just like we put in the green color in arguments here, and get back what the latest issue was up in GitHub. But where it begins to be really, really cool is what's called tool call chaining, meaning the agent begins to orchestrate the different tools in order to actually achieve the thing. So in our case, we had different people and their favorite color and their country. So we could go, for example, say, what is Ben's favorite color? And in order to find out Ben's favorite color, it knows that it needs to call get person. But in order to call person, it needs a person ID. But it then knows, because it can see the schema of how each tool is, that get persons would be able to give back person IDs. And if it can that, it will first call the get persons, find Ben, extract that his number is 1, then call get person, and then find his color. And this can go even further, so we can go in and say, change the color to Ben's favorite color. Then we'll go to get persons, get person, and then change color, because it knows that Ben had the favorite color of blue. But we could also say, and use the LLM's word knowledge, set the color to the primary color of the Canadian flag. That would work. It would turn it red. So calling tools are very, very powerful, especially when they go in and do tool call chaining. Next up is structured output. Structured output is by far my favorite feature in AI. It tells, because I looked into all my production code to check how was the different ways I called LLMs, and in 82% of all my calls in live production, it is structured output calls. I haven't told you what it is yet, so you don't know why. But of course, just to tell you, this is a very important topic. But luckily, it's also the easiest one of the features to learn. So let's get into it. And the best way to learn it is to see the pain that is when you don't have structured output. So let's imagine I needed to make an AI that showed movies. And I wanted to have that on a website. In my case, I'm just doing it in console still, but we would have the same problem. because I could go in and say, what is the top 10 movies according to IMDb? And this would be my response. It will come back with a disclaimer. It has a LLM cutoff date. They don't know up-to-date information unless we give them some web search tools. So it comes back with some text up here. Then it's actually giving the list. This is a fairly static list at the moment, so it's actually the correct one. And then it gives back that it can fluctuate on how to actually do something. But how would I show this in a GUI? How would I put in the title, the year of release, and so on? Because LLMs are non-deterministic. So if I ask it again, it might give it back in a slightly different format. In this case, it had put it in bold using Markdown, and a slightly different text up here and down here. Sometimes it will even come back and say, this is too risky to give you, but here is a step-by-step guide on how you find it yourself. Here I wouldn't be able to even get the movies. Here I get it back in a different format again, with a different model. And in this case, it thinks it's better to give back the score as well. And in a totally different format, where it gives back the director as well. So we can't really just use these LLM calls for other than doing a chatbot. If we need to have it in a more structured format, hence the name, we can't really just do this. So we need to fix this, and that is where structured output comes in. Because the solution is that we need to make some kind of class or record that says, this is how I want it. In my case, I want movies, I want a title, director, year of release, and an IMDb score. This is what I'm interested in about movies. So don't just guess if I want the director or not. Also, this is what I want. And this is just a C# class so far. But when I make my agent, it's exactly the same as before. And then when I go in and get my previous answers before, that's where I just use run async. But instead, I'm just using something called run async with a generic on. Because it's that simple. We just say, I want it back in this format. And what we just end up, instead of this unstructured text that we saw with some disclaimers up front and behind, we end up with JSON back. And in 18 Framework, it's even easier because we can just say .result, and that has a deserialized version of that JSON. So when we are here, we get our text, and it will come back in a structured format, hence the name. And when we get the result, we just get them back in the object we defined. So a movie is just a plain C# class or record, and it can even do nesting. It can do enums and all kinds of things. I haven't seen anything it can't do. Sometimes if you want dates back, you need to specify in a small description on top of that property what format it should be in. But beyond that, it knows all the data structures of C#. And this is being sent to the LLM as a JSON schema. We will see that a little later, how that actually happens in real life. And that later is now, because now we have learned the three of the four main parts. And RAG is by far the more advanced one. But before we go into RAG, let's do a little meta demo about what actually happens behind the scenes so we better understand what's going on. And this is what I call the life of an LLM call. So in here, I have sort of the same kind of code. I make a client, as we've seen before. I make an agent. In this case, I make a little tool that gets some weather in this case. So my structured output in this case is a weather response with some city condition and such things. I put in speak like a pirate. So all the things we have learned so far. There's one little line up here with some transport options. That's only for me to be able to hook into the HTTP client and log this information. So we ask what's the weather like in Paris, and we have a tool that says it's sunny and 90 degrees always. Of course, in real life, that would not be this. It would go into an API from OpenWeather or something like that and give it back. But just so we understand what is going on. And what happens is the LLM, of course, will, whenever we do this line of code, it will send a request to the LLM. In my case, it's my OpenAI model up in Azure. So it will be this URL that it has behind the scenes. And what you're seeing here is a long JSON. I've just put it up in 3 different columns because else we couldn't read it. But see it as just behind this is this, and just behind this is this. So what is actually being sent? First up, we're sending 2 messages. We only wrote one, but the first one is the system message that takes our instructions here and turn it into the system message. So while we're just sending one, there's actually 2. One from the system and one from the user. And that's just our text we had in the code. Then it shows the model. We chose that here. And then it shows a response format. This is the structured output part. And also one of the reasons why we begin to use structured output, there's more cost of tokens involved, because we're also paying for sending this to the LLM, because it will tell, hey, whenever you respond, I need to have a weather response. It needs to have a city. It needs to have conditions, meaning sunny or foggy or whatever. It needs to give back the degrees in Fahrenheit and Celsius, and all of these are required. So this is essentially what happens when we do this part here. This is being attached to the system in order for us to also know the response format. And the final thing we send is the tools. In our case, we only had one tool, but there could be multiple tools here. So we're sending a tool called getWeather. And if you want to call that, that needs a city, and that city is a string, and it's required. So that is this part over here, together with this one down here. So everything we do is actually sent to the system, and we are paying for the tokens for all this code. So even if we just said hi, we would pay more than just the 5-10 tokens hi would equate to, because we're also sending for all these. So the more tools you send in, the more structured output, the more advanced structured output, the longer system message and so on, cost more tokens. All for the benefit of a more elaborate answer, of course. And then someone will say, okay, then it must come back and say it's sunny and 90 degrees. Because that's what our tool says. But how in the world would it know that? There's nothing here that says that we couldn't. And if it was a call to a live API, of course we couldn't give that. So what it actually does is instead says, hey, in order to answer this question you have given me, I think it would be good to call this tool, meaning its finishing reason is tool calls, meaning essentially, I'm not done, because the finishing reason for it's done, it's called stop. But in this case, it says, I need to you need to give me some more information before I can answer this question. And more specifically, I think you should call the tool called getWeather, and I think you should call it with the arguments that city equals Paris. And that was easy to get from here, but imagine the user would have instead said, what is the weather in the city of the Eiffel Tower? That would also work, and it will turn it into Paris here. We then get some ID calls, some created dates, what the technical version of the model behind the scenes is, that we're using chat completion. And in terms of Azure AI, it will also give some prompt filters back, meaning some guardrails about hate speech, jailbreak, self-harm, sexual and violence. So had we done asked for something that was self-harm, it might have stopped us from getting a response back. And in agent framework, it equates to actually throwing an exception with whatever this will tell back. We get a little bit of metadata about the call itself. How many tokens did it cost? How many reasoning tokens did it cost? So in this case, it's a ChatGPT 5, so it can reason about how it should answer. Reasoning tokens are counted as output tokens, and the prompt tokens mean the input. So what we sent here cost 190 tokens for input. And what we see here is output, and we also pay for that. So what this is of course not something we can put back to our console right now. It's not our finished answer, but Agent Framework will see this as, oh, I need to call this piece of code. I need to invoke that delegate method, and it will do that using reflection. So when it calls it, it will now take its Sonia 90 degrees and turn it, make it run. You can actually set breakpoints doing this, and you could sit here and wait forever, because it's not like OpenAI right now is awaiting a call. They have just said, we need a tool call, because they're stateless. And what we need to do now, whenever we get back from this call, is we need to send a new request. And that request looks awfully a lot like the first one. The only thing that's actually changed is we have added more messages. Meaning we have added, what is the weather like in Paris? That was from the first one. And then you told me to call this tool, and here's the result of that tool. So we're sending exactly the same. And we're paying for these tokens again, because it is a stateless system. There's actually talk about change this a bit in terms of going from HTTP to WebSockets, but it's like information from today. It's not in the framework yet, but there's talk about changing this a bit so it becomes a bit more stateful. But essentially, we still need to send all this extra thing just to send this new information that I didn't know about. And once we get that, we get our response. In this case, we're using finishing reason stop. And that's because it knows, here's the message I want you to give back to the user. In our case, it's not a message, but the content of how we fill out our JSON for our structured output, our prompt filter again, and some completion tokens and stuff. But all we need is this. This is the only little thing we need in order to get our weather response or movie or whatever we want back when it comes to structured output. Had we not used structured output, we would of course have gotten back the information here in the way the LLM chose to answer back. But that's actually what's happening. It's not just one call, it's multiple calls. And if we have tool chaining, it will be multiple calls. And for every single call we do, we pay for it in tokens. So very, very powerful, but also very, very expensive in quotation marks, because we do this to get value, of course. But this is actually what's going on. It's a dumb system behind the scenes. It's simple system, whatever we call it, which is very, very stateless. On to RAG. RAG is the fourth, but also the most complex. It is bigger than all the other three combined, and for that reason, we can't go into every single little details about RAG in this session. Each individual part is not that difficult, but there's just so many different parts and so many different techniques and strategies in order to do good RAG. But I'm gonna give the basics on how it works and why we even need it in the first place. So, what is RAG and why do we need it? In short, it stands for Retrieval Augmented Generation, but that doesn't make us any wider. So let's see an example. So we can ask an LLM about a question. What is the capital of France? And it can answer. That's good. And they are surprisingly well known about all kinds of odd questions. So what is the Einstein-de Haas effect? And this is even one of the smaller models, and it can just spit out what this is about some magnets rotating stuff. But if we ask it a simple question like, what's the guest Wi-Fi password to the office? It has no clue. And why that is? That's quite obvious. It's been taught the internet, excluding some adult sites and malware and phishing and so on, all for helping us. But it of course doesn't know any personal data of yours. It doesn't know company data. It doesn't know other people's data. It doesn't know offline data. There's certain world knowledge in the world that are just not given to it. And I hope you understand that it's a good thing that it doesn't know your bank number and your credit card number and so on. So of course, it doesn't know every single little thing. But RAG is actually the process of giving it more data that it doesn't know, and we need to give it on the fly because the only place we have to give it is in either the system message or the user message. You often give it in user message, and it's your responsibility to give that data on the fly. But you don't know what they will ask for. So you give it a lot of data. And then you hope or assume that you have given the information. So if I'm asking about what is the guest Wi-Fi password, and I give it my name, my favorite color, my parents' dog's name, the Wi-Fi password, where I live, who is in charge of the port, and my birthday, if that's the extra knowledge I give, it can actually answer. It can, among all the fluff that it doesn't need to answer that question, it can extract it. Just like it can extract among all its world's knowledge exactly what the capital of France is. So RAG is nothing more than adding more to the prompt. But doing that can be hard, and it has its limitations, because if we have all the knowledge that are relevant to the LLM, some of it is easy. We might have it just at hand in markdown files, and we can easily provide it if possible. But it could also be that the only place I have the Wi-Fi password to the office is in an image. Or it could be just a piece of paper hanging out in the lunch area. So we are in charge of giving, cleaning, making the data available to the LLM. And that is just normal C# to do data washing and all the things we need. But even if that was easy and we have all the data, we might end up with some problems of feeding all that data. Because we could have thousands and thousands of conversations meeting summaries, contracts, financial data, Office Wi-Fi password, and all kinds of things. And if we fed it every single little thing, it will end up being a needle in a haystack finding it, which they are pretty good at actually at the moment. But at the same time, we could end up with putting so much data in that we hit the context window max. So every LLM have a context window. They go from normally 128,000 tokens to 1 million tokens, Google being the ones with the highest number of tokens at the moment. And that equates to roughly what you could fit into a book that was between 500 and 2,000 pages of text. So you can actually put quite a lot of it up there. But the more you put up, the more needle in a haystack it is. And the slower it will be, and the more costly it will be. So just putting all the knowledge in the company, all the knowledge for yourself onto every single prompt would probably be a bit too much. So for that reason, we need some kind of search index. We need something a little like Google on the internet. So we need to take all our data that we want and put it in some kind of search index. We then need to ask the question and search in that search index, and then among the thousands and thousands of things we put in the search index, give back the 3 most relevant for that. Just like Google can find Facebook if you search for Facebook. So if I just asked this question and these were the 3 that came back, it told me what the guest Wi-Fi is, my home Wi-Fi, and what my latest Wi-Fi bill was, because that was the ones that were most relevant to my search criteria. Then it would be able to answer without needing to get the 1,000 and 1,000 of them, but only 3 of them. And this is what RAG is. So putting the data into the search index is called embedding and ingestion. The searching is called RAG search. And what our search index is called the vector store. So vectors and embeddings is not something I'm going to go into too much, but it's essentially just finding similar items based on their semantic meaning instead of exact term matches. So if I search for kitten, it will get closest to cat, but it will get close to animals, but it will be farther from fruits. And vectors is just in a 1536 dimension vector database. We can only see have the 3 or 4 dimensions in our minds, but in math you can have multiple vectors like that. And that is called a vector similarity search. The math is beyond this course, but that is essentially what's going to happen when we do this. So we need some embeddings and we need some vectors. So what is going on is that we have the source data that we clean using C#, and then we embed them. And the embedding needs to have the LLM embedding model up in the cloud. For example, OpenAI's text medium small. And that we give a vector back. And the vector is just double values, 1,536 of them, because there's 1,356 dimensions in that specific model. Some of the models have more, some of them have less. And that we put into our vector store. And we can have multiple vector stores. There's SQL Server, there's Azure AI Search, there's Cosmos DB, and so on. Various different Microsoft and open source. We then do our question, and we then embed this question because we compare vectors to vectors. We can't compare text to vector. So we take our question itself and turn it into a vector. And then we do a vector similarity search here and get back the search result, meaning give me the 3 most vectors that are closest to the vector that represents my question. And when we do that, we can get our AI to respond. So this is now what we're going to see in code, how you do this. So first we need some data. In my case, in the sample repo, I just made 10 Q&A sessions with a question and an answer about some internal knowledge information about a company, random stuff. And among them, one of them is what is the Wi-Fi password at the office. But all the other things has nothing to do with Wi-Fi passwords, and that's all about if we have the day off on Christmas and all kinds of things you could know that could be in an internal knowledge base. And there would be 1,000 of them perhaps in a big company. Then we need the vector store by itself, and we need the embedding generator. So we have our Azure OpenAI client, and instead of making a chat client, we make an embedding client and get it as an embedding generator. We need a vector store. The vector stores comes from various NuGet packages that are part of the Microsoft Extension Vector Data family. And in my case here, I'm using a SQLite vector store. And in a SQLite vector store, the only thing in the connection string would be where the database is stored. But if it had been a SQL Server vector store, it would be a connection string to the SQL Server. Had it been a Azure AI Search, it would have been an API key to that and an endpoint, and so on and so forth. But we just get a generic thing called a vector store that doesn't care about if it's a SQL Server, if it's a Cosmos DB. It's been abstracted away from us. And then we need to put into that vector store a collection. And they have chosen the word collection because some vector stores call them indexes, some call them tables, some call them databases. There's different things for it. So in a SQL Server, the vector store or collection I made is knowledge underscore base, and that would turn into a table in my SQLite. But in a Azure AI Search, it would turn into an index. So the word collection is the best generic term they found for it. So we make one of those, and we need to tell the collection. The primary key for this is a GUID in our case, and what is represented into that collection is a C# object. And in a SQL table, it would equate to the same as the fields, but in a NoSQL, it would just be the JSON schema behind the scenes. So we make a class that represents that, give what is the vector store key, what is just data, because when we store something in a vector store, we store it both as a vector and as the real data. So we can later grab that this vector equates to this Q&A session. And then we have our vector, in this case the 1533 different dimensions. There can be multiple things about how there's various ways of doing similarity searches. There's cosine and different things. So there's different ways of saying how is two vectors close to each other. Some of them, they all tend to work between either a 0 and a 1, meaning either 0 being the closest or 1 being the closest, different implementations. Or there's some of them being -1 to 1. So there's different ways of doing this, but behind the scenes, each implementation, in this case SQLite, will make what similarity means, and in SQLite, the closest to 0, the more exact the search is, the more similar the search is. So we built that object, and then we can begin to ingest our data. So we take our collection and our data, and in my case, I'm just deleting the table and recreating it. In real life, you wouldn't do that. You would just put in the delta of what has been updated using upsearch here. But essentially we're just looping through the data and doing upsearch, taking the raw object and turning it into the vector object. And down here we don't set the vector itself, because this upsearch by itself behind the scenes will do the call to the LLM that it needs to make this vector. So once we have that, and this is something you would probably do on a schedule every night, or on a webhook or something like that, because you wouldn't do it live while the customer was searching for something. So this is a separate process. In the sample repo, it's just after each other, just to keep it simple. So now we're ready to do our search in the vector store, and we do that by making a regular agent and a regular chat loop that we have seen for the rest of this system. So we give it an instruction that it's an internal knowledge base agent, and it should use a tool to get its data. And yeah, we are making one tool, and that is the search tool that we give the collection of the vector store. And next slide we'll see that tool. But beyond that, it's exactly the same as if we called the get person tool or the change color tool. It's exactly the same. We don't need to do anything further than that. So the tool itself is also fairly simple. We just get our collection, and then we have one method on it called search. And that search takes the input, which is often just the question raw, what the customer have given. But there are certain techniques also that sometimes extract, enhance the question or turn it into keywords and so on. And that's a way beyond topic here in how you get the best vectors results back. But in a crude way, we do it here. We just say we need to build a string with the search results. And that string, if we have a look, just use the vector stores collection and it do a search. And the search takes two required parameters. First is what is it we want to search for? And again, on the fly, this search text here will be turned into a vector before it do the similarity search. And then we tell it how many search results do we want back. In our case, we had 10 records. We could hope for the best and just say it's always the top one that are the most similar that we want to use. But often you overlap a bit, saying, in this case, we want the 3 most likely ones back and use them. Then we write them out here so we can see in a sample in 1 second, but else we just build up a string with what is the most similar knowledge we want to give back to the LLM. And giving back to the LLM is just we're giving it back from the tool. So just as when it called get persons and got the people, now it actually gets the live search result from the vector store and figuring out and using that in order to do the answer. So when we do that, we can go in and say, what is the Office Wi-Fi password? It will do a search, and we said it was 3. So we can see it gave it a 1.3 for that this is the most similar. Then the second most similar was something about can't log into the Office account. That's probably because the word Wi-Fi and Office and password, or the Office and password was here, but this is still a more similar sentence when we talk about this sentence here. And that we can see indicated in the score that this is more similar than this one is. And the third one is something completely different. There's a manager. That's probably the only reason with Office and managers that this has come along, but it's have a very high score where in our case the 0.0 had we written exactly this sentence, this would have been a 0. So this is how similarity searches work. They just give back among all the records, in our case 10, which of the 3 most fit this similarity semantic search wise. And the LLM get this. This is being augmented onto the prompt, and out of that it are good enough to figure out, okay, then the password must be guess42. We spend more tokens on it because we need to on the fly put these things in. We can of course ask in a different way with some completely different words. So for example, the customer is on visit and they need internet access. Even here, the Wi-Fi password office is the one getting closest. So visit perhaps goes to guest. Had it been a different password, of course, it would have been even harder to figure this out. But internet access is equated to Wi-Fi. Customers visiting is equated to office, and so on. But you can see the similarity search is not as confident. It's a 50-50 if this is the right thing. While here it was like it's 70% secure, while only 30% unsure. Other ones come back hitting these, and it's different things. In this case, that's something with registration of internal vacation. Again, probably because of manager and approval and stuff like that. It's again, there's these 1536 different dimensions that's being evaluated. So exactly why this is, but if you ask this question again and again, you will get exactly the same. These are deterministic and compared to what LLM can do. But we get the back, and we can see that it still can be able to give our answer back. So that's good. So RAG is just a way of adding more data onto your prompt. So it's one big hack, to be honest, because we can't have everything. The LLM doesn't know it up front, and it can't have everything in its context. Had we had infinite context and it didn't take extra time, we would give everything for every single call, and then we would get a better AI. But this is the best we can do until we have that, if we ever get that. So that is the 4 concepts. A little about what I use them for in production. Chat, I rarely use it. To be honest, I have a few chatbots live, one for internal chatbots and one for external. We do a little about text translation and summarization about text, but beyond that, I don't use it too much. Tool calling, a lot of lookups, a lot of RAG searches are tools, but you could end up with lots of different tools: time tools, file system tools, web search tools, code interpreter tools, weather tools, HTTP tools that can actually call other APIs, or your custom tools that go and add something to an ERP system or a CRM system or a web store or whatever you need. Again, this is the very open-ended, and your business will determine what you need here. Structured output, the bread and butter of all this: code reviews, chatbot intents, knowledge base extractions. Almost every call I do is structured output because I want it in a better format, or I need multiple things out of a question. And then there's RAG. I put support messages in RAG. I put internal knowledge bases in RAG. I put external knowledge bases. I've taken the entire documentation data and Markdown. Personally, I put in PDFs so I can do some bank record matching. And we even put C# source code in a RAG system. putting in a private repo, so you can actually with an API. So we could make an MCP server code assistant in order to deal with RAG. So that's everything I do around here. We can go in and look at some more use cases if we have time. Beyond the main 4 concepts, there's a bunch of things, but again, they only equate to the last 10% of everything you need to learn about AI. What you've seen now, again, 90 to 95% of what you need in order for every AI you do. So even if you didn't know these, you could get pretty far. But there's other stuff. There's breaking glass options. That's probably one of the ones you would like to learn about, setting reasoning efforts on LLM models like OpenAI, if it should think a long time or short time. There's something called AI context providers to build in memory. So, for example, ChatGPT can remember your name and your favorite color and so on. We can build that in using something called context providers. We can, on the fly, add tools based on the user's question. We can begin to store the chats. We saw that the chats could be talked about who Elvis was and how tall he was. But that was only in memory. If we want to actually persist it down into files, we need to use a chat history provider. Logging, OpenTelemetry is all there if we need to. There's the entire workflow part that I didn't cover today. And there's advanced tools. For example, an agent can become a tool for another agent. A workflow can become a tool for an agent. And then, of course, is things like multimodal, where we can look at images and PDF support. So those are the more advanced things that are in Agent Framework. There's also things outside, things like web searches, if you want live web data, up-to-date information, news, and stuff like that. There's code interpreters, which are Python Docker containers up in the cloud. That can do advanced calculations for you, generate charts and stuff like that. There's file search if you want some simple out-of-the-box RAG. Both OpenAI and Azure OpenAI offer that. I tend to not use them. I want more control over my RAG and my data. But it is an option if you don't want to build it yourself. Then there's a bunch of framework integrations. There's Google's agent-to-agent protocol, which is supported. There's a front-end protocol called AGUI for easier streaming and front-end tools. There's the entire Microsoft Foundry integrations, which is some persistent agents up in the cloud. So the agents doesn't only exist in memory, but are actually persisted up there with a bunch of audit and all the enterprise stuff someone might need. There's Microsoft Copilot integrations, and there's integrations into Azure Functions in order to run all these agents up in a cheap deployment model. And then there's a bunch of non-Microsoft Agent Framework topics like batch jobs, if you want cheaper LLM calls but can wait. There's agent skills, which is the new hype right now. There's audio and image generation, which Agent Framework doesn't do, but the raw clients do instead. There's different formats, like one of the new formats that are building up right now is called Tune, which is a better and AI optimized data format that feels less than JSON. So all kinds of things extra that you can do. You can also use some extra of mine. I have made something called Agent Framework Toolkit, which is a bunch of NuGet packages on top of Agent Framework by itself, which make it more opinionated. We saw that they were using these raw clients and didn't want to change the format. one bit after the fact. You have made the agents, and that makes some of the agents quite hard to make. So for example, if you want an agent that can do all kinds of advanced stuff, you might end up with 56 lines of code just to set that up, while putting my opinionated packages saying, yes, I know that you are a generic tool, but I know that I'm working only with Azure OpenAI. So setting things more easy and getting data more easy. So going from 56 lines of code down to 70 lines of code. So I have these for various different providers if you feel you want. All the small things that Microsoft haven't had time or won't do because they need to be 100% backward compatible. If you want more in general, I have 2 resources other than this sample repo that you will get. I have a Udemy course, which is an 8-hour version of what you have just seen. So if you feel like you're ready, you don't need this. If you feel I need a bit more details on everything, then this is the way to go. Or if you want to dive into my YouTube channel, there's 200 plus videos about all the news in AI, the protocols, the deep dives into some of the more advanced stuff that we saw in the Beyond concepts. So lots of additional things, but in my mind, you have what you need and actually to go home now and get started. We are 90% of the way. And the most important thing is to just go home and do some little thing, because that will inspire you to do more and more and more in the system. So with that, thank you, and we're ready for questions.